Namaste. Welcome to the next video of Machine Learning Practice course. In this video, we'll continue our discussion of Scikit-learn utilities for data preprocessing. The next set of utilities are for feature selection. There are two broad classes of feature selection methods: filter-based methods and wrapper-based methods. Let's first look at the filter-based method. The first method is about variance threshold, which selects feature based on some kind of a variance threshold. So variance threshold is part of feature selection module from Scikit-learn. So we can import variance threshold from Scikit-learn.feature selection module. And we also specify what is the threshold of the variance. So here we have specified variance threshold to be 9. So what will happen is that features that have variance threshold greater than 9 will be selected. So we call fit_transform by giving it the input feature matrix. So here you can see that we have selected the second column, which has got the variance of 67. The first column, which has got variance of 1.25, is kind of rejected because it violates basically the variance threshold that we have set over here. The next filter-based technique is select k-best, which is again implemented as part of feature selection module in Scikit-learn. Here we are going to use mutual info regression as some kind of a scoring function. So there is another option that is available to us, which is F regression. So here we are going to use mutual info regression. We will demonstrate this on California housing dataset, and what we do is we instantiate a k-based object, select k-based object with the scoring function, which is mutual info regression, and we also specify how many features we want to select. So here k is equal to 3, so we are going to select 3 features. So we call fit transform on the feature matrix and the label vector. And you can see that the shape of the feature matrix after feature selection is there are exactly 3 features that are selected. The original shape was 2000, 8, so there are 2000 samples because we selected here first 2000 samples from the California housing dataset in order to perform select k-best, and there were 8 features. Now it has reduced to 3 features. We can look at top 3 features by calling get_feature_names_out method on the select k-best object, and you can see that the first feature, the 7th feature and the 8th feature are selected as part of mutual info regression scoring function. In the similar manner, we can also use select percentile method, and select percentile is again implemented as part of feature_selection module. So in select percentile, it works pretty much like select k-best. We have to specify the scoring function, and we have to specify the percentile, the top percentile features that we want to select in our model. So here we want to select top 30 percentile features. Again, we perform fit_transform. You know, this fit_transform we are calling on each transformer object because that is the method that we use for transformation. So fit basically learns the parameter of the transformation process, and transform actually transforms the dataset into the transform dataset using the parameters that were learned as part of the fit process. So you can see that after transformation we have 3 features, and remember the original number of features were 8. And select percentile also select exactly the same features that were selected by k-best. So you can see that it was x0, x6 and x7, and the same 3 features are selected by select percentile. Then we have generic univariate select, which is again implemented as part of feature_selection module. And here also we have to specify the scoring function, we have to specify the mode, and here we have specified mode as k-best. There are some other options like we can select percentile, we can select FPR, FDR, FWE as modes, and we have to specify how many features we want to get, how many features we want to select. And here we used k-best as the mode, and we are selecting 3 features based on mutual info regression scoring function. The next class of feature selection methods are based on wrapper. So wrapper based method uses an estimator object and then it ranks the features. The first one is recursive feature elimination. There are 2 steps. It first fits the model and then ranks the feature. Afterward, it removes one or more features depending on the step parameter. So RFE is also implemented in feature selection module. So we instantiate an estimator object which is linear regression, and then we call RFE with estimator object, number of features to select, and the step as parameters. We call fit on the selector, which is the RFE object, by providing the input feature matrix and the label vector. Then we get support. So once this fitting is done, we get a Boolean array in support underscore member variable that tells us which features are selected. So Boolean array, if the corresponding value is true, that feature is kind of selected. So here we are selecting the first feature, the 7th feature and 8th feature. Those 3 features are selected. And we can also get rank in ranking underscore member variable, and in this case if value is 1 then the feature is selected, and features with rank 2 and onwards are kind of not selected. Then we call transform on the selector in order to transform the data set. So now after transformation we have the housing data set with 3 features. So there is another technique called RFE-CV which works exactly like RFE except that it adds another layer of cross-validation on top of RFE. Next method is select from model, which is also implemented as part of feature selection module. It uses an estimator object which is trained on the input feature matrix and a label vector, and then we instantiate select from model by specifying the estimator, number of features to be selected, and it selects top 3 features based on the feature importance. Because here we have specified max features equal to 3. And the last method is sequential feature selection method that selects or deselects feature one by one in greedy manner. There are 2 modes, one is forward and second is backward. In the forward mode, it starts with 0 feature and goes on adding 1 feature at a time until the desired number of features are selected. And in the backward mode, it starts with the entire feature set and then goes on deleting 1 feature at a time until the desired number of features are remained. So here interesting thing to observe is, let's say if you want to select 3 features, we will do it with forward and backward mode, and we will record the time. So here the wall time is 227 milliseconds in the forward mode, and we do the same thing with direction equal to backward, and in backward mode we are taking a longer time. Now we want to select 3 features out of 8 features. So in forward mode we are going to go on adding features one by one, so there are probably 3 iterations that are required. But whereas in backward mode probably we need more iterations because we need to delete 5 features in order to get 3 features. So depending on the number of features that we want, we can either use forward or backward mode, whatever makes sense. That was about feature selection. We can also perform feature selection through principal component analysis. Here, in fact, it is called feature reduction. So what we do is we perform dimensionality reduction. So we want to reduce number of features through a method called principal component analysis. So here we will demonstrate principal component analysis, for which we have generated a synthetic dataset which looks something like this. So PCA is part of sklearn.decomposition module, and we can call PCA with number of components as an argument. Here we want two components of principal component, or we need two principal components, hence we are specifying n components equal to 2 in the PCA object. And then when we perform principal component analysis like this with PCA, by calling the fit function on PCA, we get two components, and these two components are kind of represented in columns of the output feature matrix. We can look at these principal axis. So these columns are also called as principal axis. So we can get to know what is the variance that is captured by each component. The first component captures 76% variance, whereas the second component captures 1% variance. And this is the direction of the first component, one in the red, and C2 is orthogonal to the first component. So subsequent principal components are orthogonal to the first principal component, and we have shown this additional vector just for the comparison purpose. We can check the variance covered by different vectors. The maximum variance is covered by C1, and then C2 covers much lesser variance than compared to C1. Now if you want to reduce the number of dimensions from 2 to 1, what we do is we instantiate PCA object with number of components equal to 1. Then what it does is it selects the first principal component and transforms data onto that component. So we call PCA, we call then the fit function on the instantiated PCA object by providing the feature matrix, and then we perform the transform. We call the transform function on the feature matrix to get the transformed representation. So you can see that after transformation we have selected one feature, so number of features are reduced from 2 to 1 in this case. And we can look at the data in the new feature space. So the original data is with the blue dots here, and the projected data on the first principal component are in red. So you can see that this is how the projected data looks like. It is in the direction of the first eigenvector. So first principal component is always in the direction of the first eigenvector, and it captures maximum variance in the data. And the way PCA works is once it finds this component, it basically projects the data on this component and gets us the new feature representation. So we learned about different preprocessing utilities. These preprocessing utilities have to be applied in exactly same order on training, evaluation, and test set. If we do not do it, then that would lead to incorrect predictions, because the model might see different distribution of the data than what it saw in training, for example. So a sklearn pipeline module is a very important utility for us to build composite estimators as a chain of transformers and estimators. So pipeline, what we do is here we are defining a pipeline object with two steps. The first is simple imputer that detects and fills up the missing value, and second one is standard scaler, which is used for scaling the features. So now we have pipeline with two components, imputer and standard scaler, and we can instantiate pipeline object with steps equal to this particular list of tuples, and there are two parts. One is the identifier and second is object, which could be transformer object or estimator object. So there is one caution that we have to follow, or we have to observe, that the final estimator needs to implement the fit method. So whatever is the final estimator, it has to implement the fit method. The intermediate steps must be transformers. That means they must implement fit and transform method, but the final one has to implement only the fit method. So you will normally see estimators as the final step, and then there are a bunch of transformers that will form intermediate steps. We can also make use of make underscore pipeline function in order to define the pipeline. This is another example of pipeline where there are three steps. Simple imputer, we first fill up the missing values, then we perform principal component analysis, followed by that we call the linear regression estimator. Here number of steps in the pipeline is 3 that can be accessed with pipes.step, and calling the len on that, pipes.step will return an array. So now there are different ways to access, let's say, the second estimator here, or for that matter any estimator. So the second estimator can be obtained by calling named step, where we give the name of the step, which is PCA in this case. So if we do that, we get the estimator, or we can access it from steps, and the first index in the step is basically PCA estimator or PCA transformer. Then we have pipe 1 again gives us a PCA transformer, or we can call it in a dictionary syntax. We can access the parameters in the pipeline by giving the name of the transformer, which is PCA, or an estimator for that matter. So we use here, if we want to, let's say, set number of components in PCA, then the way to do that is we use this identifier for the PCA, then there is double underscore, and then there is a name of the parameter of PCA, which is set to 2 over here. This is how we can access parameters of different steps in the pipeline. And this will be useful for performing something like grid search, where we have to specify the parameter grid. In order to specify the parameter grid, we need to use we need to access the parameters of transformers or estimators in the pipeline. Here we perform grid search by specifying a parameter grid, and in parameter grid we want to try different imputers, then different values for CLFs, and then we also want to perform the parameter search on the parameter of CLF, which is the C parameter, and this is how we can access the C parameter, CLF underscore underscore C, and this sets the C parameter of the CLF step in the pipeline. And then we perform grid search. We'll see the details of grid search in the next module. And finally, we will see how to cache the results of the transformation steps. Transformation is kind of an expensive operation, and we can cache the results of intermediate computations. And here we have to specify the memory parameter where we want to store the results, or where we want to cache the results. Finally, we have another utility called feature union. It applies a list of transformer objects in parallel and then concatenates their output side by side to form a large transform feature matrix. So feature union and pipeline constructs can be used to create complex transformers. So here is an example. So we have two pipelines, one for numerical objects and second for categorical objects. So we are using basically we are using the column transformer, then we have missing value imputation followed by feature scaling, and then we have label binarizer on the categorical input. Now what we do in feature union is we specify the list of transformers where there are two transformers here. One is numerical pipeline and categorical pipeline, and that gets us a full pipeline. When we call this full pipeline on the input data, we get a transformation which is obtained by applying numerical pipeline and categorical pipeline to the respective features. So you can see that the numerical pipeline is applied on first 4 features, whereas the label binaryzer is applied on the fifth feature. And this is some kind of a visual representation of how feature union is going to work. So there are two pipelines. It first selects the first four columns and then applies imputer and feature scaling. Then the fifth column we apply what is called as label binaryzer, and fifth column is specified over here with the index. There is one final topic which is very important, which is about imbalance data. So in many real world cases you will encounter this problem called imbalance in the dataset. So typically what happens is that there may be some labels or some classes that are overrepresented while some classes are underrepresented. We have very few number of examples for some classes and we have large number of examples for the other classes. And when we have such a situation, we call it as an imbalanced dataset. And imbalanced dataset might lead to less efficient ML models. So ML models might overestimate or underestimate certain classes depending on their distribution. So there are two main approaches to handle imbalance in the dataset. We can either undersample large datasets, or we can undersample the examples that are there in abundance, or we can oversample the examples that are few in the training set. And we'll see how to perform undersampling and oversampling. So if we are doing undersampling, what is happening is we are throwing away many examples, we are not selecting them, and we are selecting a dataset which is much lesser than what is available to us. Whereas in oversampling, what we do is we increase the size of the dataset by oversampling the minority class. So the minority class is oversampled by copying over the examples or generating more examples synthetically, looking at the distribution of the minority class. Again, we demonstrate this on the wine dataset, which is kind of an imbalanced dataset. There are too many examples of wine quality 5 and 6, whereas too few examples of something like quality 3 and 8. And again, for class 4 and 7 also we have few number of examples compared to fewer examples compared to these two quality labels. So we can perform undersampling with random undersampler from imblearn dot undersampling module, and here we basically what we have to do is we basically have to call fit resampler on the random undersampler object. So here the original dataset shape, so basically there were 681 examples in label 5, 638 example in label 6, and so on. And after resampling, we have 10 examples each of every label. And we selected 10 examples because 10 were the least number of examples that were present for any label. So here 3 was the label with the least number of examples. So this random undersampler has selected 10 examples each of for each class. So you can see now that the dataset size is reduced substantially compared to the original dataset. In other case, we can do oversampling, and there is a random oversampler present again in imblearn.oversampling module. We instantiate random oversampler and we give the input feature matrix and the label vector. You can see that after resampling, we have 681 examples each for every class, and the 681 was basically the maximum number of example present in any class, which was in case of class 5 or quality 5. And here now we have 681 examples each for every label. So SMOT is a very famous technique or a popular technique that is used for oversampling. It is also available in imblearn library. So SMOT is synthetic minority oversampling technique. It oversamples the minority class. And you can see that after using SMOT and oversampling, SMOT oversampling, we get again 681 examples for each label. So there are different type of SMOTs: borderline SMOT, borderline SMOT SVM, and adaptive synthetic sampling. So SMOT is a very popular technique that is used for oversampling. So this is how you can handle the imbalance data set. So before you proceed with any model training, first we have to correct for the imbalance, and then we can use this data set for any kind of subsequent model training. So that's it from the data preprocessing tools in Scikit-learn. So now you have a better understanding of how to use these tools on real world dataset. We'll be using these tools throughout our practice course.